Okay, well, I just gave some homework back. Let me see. I think I wanted to make a few comments about it. First, I've got the solutions for you for both the written and the program. Just wanted to make a comment about the program. I mean, I'm going to be a little bit more picky now. You know, if you do something that's obviously something that I consider sort of not really the best way to do it, like
10 minutes.
Right, exactly. Well, I wasn't gonna mention the guilty party, but I mean, when you can do something instead of doing something in a loop, if you do something 8 times by just copying and pasting the same thing over again, it needs to be in a loop. That's no good. So anyway, and also I encourage you to look at my solution for this counting problem in binary, because a lot of you guys are using whole lots of unnecessary if statements all over the place, and I think it would be really good for you to study how, at least, I mean, I'm not saying this is the best solution, but you try to be as concise as possible. So, okay, so how about homework for today? You got to have another assignment for today, right? And it was a program plus some written. And some of the written exercises were in Chapter 4. We didn't quite get to Chapter 4, but we can do it the first part of it really quickly here in a minute, and show you how that stuff works.
Did we go over rotate yet?
Did we do rotate?
We did shift.
We didn't do rotate?
I don't think we've done rotate yet.
We did arithmetic shift, and that's it.
Do I not have a slide for rotate?
Oh, because we would have gone over it.
Yeah, because I went through all my slides. Maybe
I
not.
had to go back and read through
I had to go
it.
back and read.
Well, but did you get it all right
Yeah.
by reading? I'll just let you read
It's
about that.
similar.
Yeah. Yeah, only difference is you're not shifting
A 0 in.
a 0 in, right? Yeah, the C bit's just rotating around. Yeah, I think I'll just let you read about that.
Yeah.
You can do that. But good point, anyway. And then, of course, the C bit is affected with that one, but the V bit would not be, right?
Right.
Now, also, any questions about the program that's due today? Because I have a big hint. I should.
Program just converts, right?
Yeah, but let me here. I wasn't going to bring this one up, but I will. Here, let me show you this one slide that is a big hint on how to do this program easily. The problem that you have to do in the program is to input, again, the same way that we did before, an 8-bit binary number, and you use the same input technique. But this time, instead of counting through the next so many numbers, what you want to do is, assuming that it's a 2's complement binary number, I mean, assuming that it's assigned integer, write out output what the decimal value is. Now look, you guys, one really complicated way to do this is to first inspect the sign bit, and if the sign bit is 1, then invert and add 1, and then or if the sign bit is 1, find out where the zeros are and and add them up, where the zeros are, and then add 1. But that all of that is, if you think about it, it's not, you don't have to do all that stuff. Now, if you've already did it that way, that's fine, but just here's it. But I mean, look, you guys, look here at figure 3.13. Look at figure 3.13. Now, you see, it's like breaking the number line in the middle and then shifting the right part to the left side. Now, look, you guys, all you have to do is convert the number as if it were a positive number, as if it were unsigned. Are you with me? As if it were unsigned.
Right.
And then if its value, if the value of that unsigned number is greater than
What it should be. Its range.
Yeah, is greater than, it's this positive range, is all it takes is just one line to shift its value down. I mean, to make it be the negative one.
You just
All that.
Look at what
take the positive range and subtract whatever.
you just subtract. Yeah, it's all you have to do is just subtract a key number from it, and boom, it's done. You don't have to have an if statement and do it one way if it's one way. You do it in decimal. You see what I'm saying? You could do that in decimal. I mean, you could convert it as if it were unsigned and then just make just one little decimal adjustment. But that's just something for you to think about. You don't have to do it that way.
The first number after, beyond the positive range, becomes the lowest negative number, right?
Yeah, but it will all work out if you.
Just changed it to negative right here. At the end of the else.
It will all work out. I mean, everything will work just with that. It's just one if statement. You only have to do it one way, and then it's just one if statement to make an adjustment, and boom, it's done. But, I mean, so you might be kicking yourself if you already did it the other way, but
No, I
that's all
shouldn't
right.
have done it.
Why we should procrastinate?
I know.
Yeah. Oh, no. That I should not be encouraging you to procrastinate while I give you the hint on the very last day. But this will never happen again. Everything, you know.
I feel like it always happens.
Yeah, it always happens. Okay, so let's go. Let's do this material in chapter 4. Were you guys able to read ahead and get the exercises done anyway?
There's only one, right?
Yeah, but I mean, you had to fill in some blanks, do some stuff.
That one I procrastinated on.
Okay. Okay, so what are the 4 parts of a computer?
The CPU.
The input.
Input,
Main
Input.
memory.
CPU, memory, and output. And what are they all connected with?
The bus.
The bus, and what's a bus?
Bunch of wire.
Bunch of wires. Okay, so here it is, figure 4.1. Only now, in addition to having the data flow, we also have these wires, another set of wires here called control. Now, look at what the control, we've already talked about how the data flow connections work. But what do you notice about the control lines on this figure 4.1?
They're done.
Well, they're dotted, yes. What else? That's how you know they're
They come out of the CPU and into everything else.
Yes, they come out of the CPU and into everything else. What does that mean?
CPU controls them.
That means that the CPU controls all the other parts of the computer. Are you with me? So that's why it's called central processing unit. It's the center that controls everything. Are we good? It's a little bit of a simplification, but for the most part, that's it. Okay, so now what we're going to do is we're going to look at the 4 parts of the computer, and we're going to start with the central processing unit, the CPU. Now, let me make a few comments right here. Now we have a dilemma. Okay, here is our dilemma. Who made the CPU for that computer right there?
Apple.
No, not the CPU. Apple did not make the CPU.
Intel?
Intel.
Okay.
Intel made the CPU. Okay? And does anybody have a phone?
Yeah.
Okay? Do you know who made the CPU for that?
Nokia.
Is it
No,
AMD?
Nokia?
Is it AMD or Intel? Or?
It's not Intel. I mean, 99.9% of the CPUs that are in these phones are, it's not Intel, it's a chip called ARM, A-R-M. In fact, there's probably more of these processors than there are Intel processors because there's a heck of a lot more phones than there are computers in the world.
Is that true?
I might should take that back. There are a lot of computers in the world. But what I'm saying is, the Intel chip by no means has a monopoly. I mean, you know, it's, okay. This stands for Advanced Risk Machine, actually, ARM. But we have this dilemma because when we learn how a CPU works, should we learn, you know, how the Intel chip works, or should we learn how the ARM chips works, or should we learn how some other chip works, you know? Okay, so there's another one, MIPS, M-I-P-S, is another chip that's different from the other two, okay? So now here's the thing. We could either pick one of those chips to learn, in which case, if you ever had to deal with the assembly language of another chip, you'd be learning one and not You wouldn't be learning the one that you would, yeah, you wouldn't know that one. Okay? That's one problem. And another problem is all of these chips that are in the real, real physical chips, they are very complicated. There is a certain set of fundamental principles that all chips have in them, okay, implement. All chips are basically designed the same way, but the details are way different, and it's way complicated to sift through all those irrelevant details to get to the heart of the matter. You see what I mean? So the other alternative, instead of picking a specific chip to study, a specific CPU to study, is to study a CPU that's designed to teach the concepts. Are you with me? Now, the disadvantage of studying a chip that's designed to teach concepts is that now it's guaranteed that whatever chip you need to work on, it's not going to be the one that you learned. On the other hand, if you study a CPU that's designed to teach concepts, then it's a whole lot more efficient in your, we won't have to deal with, it'll be easier for us to learn it because we won't have all these complicated details to mess with. You see what I mean? So that's what we're going to do. And the CPU that we're going to study is called PEP8. PEP stands for, obviously, Pepperdine. So it's a CPU that I designed and that I've been using this for like decades. Now, the reason it's 8 is because it's in its 8th version. It started off PEP 1, PEP 2, PEP 3. It's gone through 8 different iterations.
Do other places use PEP8?
Oh yeah, yeah. The book, yeah, it's the basis of the book. This book actually uses two. It uses PEP8, and then it does use a real-world chip called MIPS, but it only does that in the last chapter.
What does MIPS stand for?
MIPS, M-I-P-S. I think you've got me there. I think it's pipe. Let me see. I think this is pipe. I think the P is pipeline. I used to know this, and I will know it for the next class. I will know it for the computer organization class. When we get to there, I'll look it up and remember. I think it might be. Yeah, it might be in there. You could look up MIPS. You could Google it. You could Google MIPS and see what it stands for. Actually, why don't you do that? As long as you got a computer up here. Yeah, so we can get it on. Can you Google MIPS CPU or something like that? Go to Wikipedia.
You should tell us.
MIPS Technologies?
MIPS, Google MIPS CPU or something like that. And then see what the acronym stands for. I'm pretty sure the P is pipeline. So M-I-P-S. Has anyone found it yet?
Microprocessor without interlocked pipeline.
Yes, that's it. Say it again. Microprocessor.
Yes. Without interlocked.
Without, yes, interlocked
Pipeline stages.
pipeline stages. Yeah, this is in contrast to the Spark architecture, which, by the way, is on its way out. Now that Oracle has bought Sun and Sun no longer exists, there was a Spark. Yeah, the interlocked pipeline, the Sun's pipeline stages were not interlocked. That was a big design feature, and then they put that in the acronym. So anyway, that's what that stands for. So yeah, and other schools use the book, and the book is based on, PEP8, yeah. So now what that means is that instead of studying a physical machine, a chip that actually has been manufactured on a piece of silicon with a chip, that you can plug in, it doesn't exist in hardware, but it does exist in software. Now, what's the most famous virtual machine that you know of? The what virtual machine?
Java.
The Java virtual machine. So in the same way that Java has a virtual machine that executes Java programs, you know, PEP8 has a virtual machine that executes PEP8 programs. All right? And you can download that. That's what we're going to do. You'll download that. You might as well download it now. The link is on the web page. You can download it, and we'll run this week. You will write your first machine language program using the PEP8 virtual machine. Okay. So on this next slide, we're going to look at the CPU. But the CPU that we're going to look at, and this computer that we're studying, is this virtual machine. Okay. So here we go. Now, again, there are a few slides that are, a few figures that you just absolutely have to memorize. This one you just have to know the registers that are in here. Okay, so now there are 1, 2, 3, 4, 4, 5, 6 different registers in here. Figure 4.2. First, there are the 4 status bits. These are the bits that you already learned about, NZVC. Okay, each one of those boxes is 1 bit. Okay, now the second register, these are memory locations that store, these are memory cells in the CPU. The second one is called the accumulator, abbreviated with the letter uppercase A. And how many bits are in there?
16.
16. And then the next one is called the index register, denoted by the letter X. How many bits?
16.
16. Now, what do you think the index register is used for? Indexed register. What has an index?
Arrays.
An array has an index. So that's because arrays are a fundamental data type in the hardware. Okay, is everybody clear on that? So the index register, in fact, the index register is used to store the index of an array. Okay, and then the next one is called the program counter, abbreviated by PC. How many bits? 16. The next one is, oh, by the way, and what does the program counter keep track of? Oh, those of you who took paradigms, what is a process?
A state.
No.
It's a program at runtime.
Yes, it's a program during execution. And what do you specify in order to specify a process?
An ID.
No.
Yeah, well, it has a process ID, but what do you have to keep track of
Where
to keep?
it's at.
What do you mean where? What do you mean where it's at?
Where it's at, like in the code, like next.
Yes.
Execute.
Yes, it's the next statement to execute. It's the next. This PC is called the program counter, and what do you suppose it stores?
The next statement to execute.
Yes, it stores the address of the next statement to execute. Now, you got to know that. You got to know this. That's the program counter. Okay. The next register is called the stack pointer. It's called the stack pointer, abbreviated SP. All right, you guys. Whenever a program executes, particularly when you call a function,
It's location on the stack.
yeah, what stack are we talking about here?
Runtime stack.
The runtime stack. So yeah, guess what SP is? That corresponds to top. Remember how when we did stacks and data structures, we had a top and it was an integer that pointed to the top of the stack? This is the hardware equivalent of that because it has to maintain the runtime stack in memory. And so this SP is the stack pointer, which points to the top of the stack. What's the next one?
Instruction.
Instruction register, IR. What do you suppose the instruction register stores?
Instruction.
Instructions. Now, how many bits are in the instruction register? 24. But they're grouped this way for a reason. The first 8 are on the top, and then the second 16 are on the bottom. All right? So what happens is instructions come in 2 different flavors. There's 2 different flavors of instructions, chocolate and vanilla, actually. Unary and non-unary. So unary instructions are instructions that have just 8 bits. Let's jot this down. Two types of instructions, unary unary and non-unary. Now, let's do, so and unary is 8 bits. 8 bits, how many bytes is that? 1 byte. And non-unary are, how many did you say altogether?
24, so
20,
16.
24 bits. So how many bytes is that?
6. Oh,
Bytes,
3.
3 bytes.
Okay, so non-unary would use all 3.
Would use all 3 bytes.
Right.
A unary instruction only uses 1 byte. A non-unary instruction uses all 3 bytes. So there might be situations in which the instruction register stores just 1 byte and the rest of it is just like ignored. You see what I mean? But in other situations it would store all 3 bytes, all 24 bits. Is everybody clear on that? Okay, so that's what is in the CPU, the central processing unit. The next, now what's another component? What's another?
Memory.
Memory. So here is a picture, figure 4.3, of main memory. Now, here is what you need to visualize about main memory. You know how whenever you go to the post office, to the mail services here on campus, and you walk into that room and what do you have? You got this whole row of what?
Boxes.
Boxes, mailboxes. The way to visualize this is that on the front of every mailbox is an address. What is that address? That's a number. It's an integer, right? So what you should do is you should imagine that mailbox, every byte in main memory is like a mailbox and it has an address on the front, and that's different from the content that's inside the mailbox. Are you with me? So you got to keep straight the address from the content. The address is the number like an address on a mailbox in the front, and the content is like a little piece of paper with a number on it, with data on it inside the mailbox. Is everybody clear on that? Now the way in figure 4.3, the way this is all laid out is, it's laid out such that the address is a 4 hexadecimal digit number. You see the address of the first cell in the upper left is 0000, that's hex. And then that byte is 8 bits. Are you with me? And then the second one is addressed 0001, and the next one is 0002, and the next one is 0003. Does everybody see how that works? And what's the last one? What's the address of the last one?
All F's.
FFFF. So in binary, what is that? 1111, 1111, 1111, 1111. So how many, can you tell from that how many bytes there are in the main memory of the PEP8 CPU?
4.
How many bytes? Good grief, there's 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9 showing right here, not counting all the dots of all the ones in between. How many bytes are there? Well, no, can you be more, no, you need to be more specific, not just a lot. Exactly how many? How can you tell? What would you have to do? What would you have to do? You have to count 1111, 1111, 1111, 1111, right? Like this.
1,
So this, what is this? 1, 2, 4, 8.
16, 32, 64, 128.
256.
256,
512.
512,
24.
1024. Okay, so now this 1024, that's 1K, right? So what is this?
24.
2K.
Right, 2K.
What is this?
4K.
4K, 8K,
16.
16K, 32K, and then the next one would be what?
64.
64K, which is how many it is. Are you with me?
It's just under that.
It's just, well, but when you count the 0,
And it adds up to it.
yeah, that's how many there are. Does everybody see, did everybody get that? So how many bytes are there? You got it?
The value is just under
The va-
60K, but
But when you count the 0, 0, 0, 0, that's another one, so it's exactly 64K. Of course, a K is 1024, so it's 64 times 1024. Does everybody see that? So how many bytes in memory are there?
64.
Yeah. So there are 64K 64K bytes
In our PEP 8.
in our PEP 8. And there can be no more. Why not? Because our addresses, because how big is our addresses? How big are our
64K.
how many bits in an address?
8.
No. In an address.
Sorry.
How many bits in an address?
Yeah, 16.
16 bits in an address. So we can only access up to 64K bytes. Is everybody clear on that? Now look, you guys. What does it look like on this figure 4.3? How does it look like the bytes are grouped? On the first line is how many bytes? Up here on figure 4.3, how many bytes on the first line? 3 bytes. How many bytes on the second line? How many bytes on the third line? How many bytes on the last line? 2. So this each one of these combinations can occur in a program listing. Okay, you understand that electronically they're not grouped like that. They're grouped like this for our convenience. And are you with me? Does everybody see what we're saying here? Because you know, what did we say a minute ago had 3 bytes in it?
Instructions.
Yeah, an instruction. What kind of instruction has 3 bytes?
Non-unary.
Non-unary. What about the second row? The second row, there's probably like a unary instruction. The third row is maybe like a non-unary instruction. You see what I mean? Okay. Is everybody clear? But now if we have some data, instead of having instructions, suppose we have data. Well, how big is our accumulator in the CPU? 16 bits. How many bytes? 2 bytes. So the data is frequently stored 2 bytes in a row. You see what I mean? Okay, but now look, you guys, we don't want to have to draw each individual bit cell. So typically, the way we would draw main memory would be as in figure 4.4. Now in figure 4.4, look at what you deduce here. In figure 4.4, you have the addresses over on the left-hand side, and you have a cell, but those cells are the same physical width. But that same physical width does not mean that they have equal number of bytes.
Right.
How can you tell how many bytes there are in the first and the top cell of figure 4.4?
The space between it and the next register.
Yeah, you have to look at the address.
That's a non-unary.
You know it's 3 bytes.
Yeah.
How do you know it's 3 bytes? Because the address of the second one is 0003 and the address of that one is 0000. So that means that first one has to have 3 bytes in it. Does everybody see that? How that works? And how do you know that there's only 1 byte in the second cell? Because from 0003 to 0004 is just 1. Yeah? Is everybody clear? Okay, so from that, here, let's see. How many the cell labeled 000B, how many bytes are in there?
2. So
How do you know that?
because this is only 2 different distances
Between B and D.
So it's either an accumulator, an index register, or a program.
Well, no, hold on. It's not it's the register. Yeah, let's make sure we got this straight. The registers are in the CPU.
Right.
This is main memory. This is a different part.
Okay.
But it could be data that's going to go into the register. Just to make it,
Yeah.
just to be
That makes
precise.
sense. That makes sense.
Okay, is everybody clear on how this, on how you can tell, you know, by the difference between the hexadecimal values. Now, I have another question for you. What's the address of the first byte on the first line? 0000. But wait a minute, there's another byte on that first line. What's its address?
0001.
And what's the address of the third byte?
0002.
2. So even though you have a 0000 as the address, that's only the address of which byte?
First.
The first byte. The other bytes have have different addresses on that same line. That's the address of the first byte. Is everybody clear? Now, on figure 4.5, what we have is an example of having each cell have a certain content. Okay, so in part A of the figure, the content in binary is shown for cell 000B, and also the content in binary is shown for cell 000C. And there are just some random values in there, right? So some binary values. Are you with me? So now do you see in part B of the figure, instead of drawing it in binary, what do we use hex for?
Abbreviation.
Abbreviation. So we abbreviate that binary bit pattern as so. You see where the 02 came from?
Yes.
And did you see where the D1 came from? Okay. And so we put, so to abbreviate that, we put 000B has, its cell has 02 value, and 00C, its cell has D1 value. But then what happens is, we don't want to have to draw the boxes, right? So in a program listing, what would this look like? Well, in a machine language listing, what you would do is you would have the address on the left and the content on the right. But you have to make sure that you don't confuse the address with the content. So do you see then in part C of the figure, we have 000B for the address, and the content is 02D1. Now, do you remember, though, when you look at this content in a machine language listing, do you see that even though the address says 000B, what is the address of the D1?
000C.
Yes. Are you with me? Is everybody clear? Okay, so that's how the bits are organized and structured in the computer. Now comes another big concept. Every computer has wired in to the CPU what is called its instruction set. Now this should sound familiar. Where have we heard instruction set before?
CPU.
ISA 3.
ISA 3 is the name of the level. It's called the what? Instruction set architecture level. So this instruction set that we're doing for PEP 8 is the instruction set for this computer. Now if you have like an Intel chip, you know, an x86 type chip, it will have a different instruction set. And if you have the MIPS, it'll have a different instruction set. ARM has a different instruction set. Are you with me?
But they all do this-ish.
They all, yeah, this part is all the same. I mean, this program listing is all the same. Yeah. But the instruction sets are different. Now here on figure 4.6 is a list of all the instructions in the instruction set of PEP 8. Fortunately, you don't have to memorize this. On the next exam, this table will be given to you.
Sweet.
All right? And look, we said that some instructions were unary, some instructions are non-unary, right? What happens is, each instruction always has, here, let's go back to here. This unary instruction has just, a unary instruction has just this first byte is called the instruction specifier. Whereas a non-unary instruction has two parts. It has an instruction specifier, but it also has a second part called an operand specifier. Okay, so all instructions, regardless of whether they are unary or non-unary, have an instruction specifier, which is how many bits?
3. Oh, 2.
8.
Bits?
8.
2, 3, 1, 8, 5. Hike. All right. So anyway, 8. But yeah, that's tricky because I'm throwing around bits and bytes and you don't know which one. Okay. Yeah. Yeah. Okay. So instruction specifier, operand specifier. Every instruction has an instruction specifier. So in this table, what do you suppose is shown over here on the first it says instruction specifier. Are you with me? So that's 8 bits. So take a look. If these 8 bits are 0000, 0000, that is the stop execution instruction. You see what I mean? Now and you see there's a 0000, 0001, and so on. Da, da, da. But now here's an interesting thing. Look at this next little group. the one that says branch unconditional. That's 0, 0, 0, 0, 0, 1, 0, A. Now what do you say? Wait a minute, A? I thought it could only be ones and zeros. What do you suppose that means?
It doesn't matter if it's a 0 or a 1.
Well, what that means is this is an abbreviation for two instructions. One of which is 0, 0, 0, 0, 0, 1, 0, 0, and the other one of which is 0, 0, 0, 0, 0, 1, 0, 1.
So it does both.
So there are two branch unconditional instructions. They are both branch unconditional, but one has a 0 as the last bit, the other has a 1. So does everybody see that that's an abbreviation for actually are you with me? And same way with the branch if less than or equal to. That A could be either a 0 or a 1. Does everybody see that? Now moving on down in the table. Also, there is a bitwise invert register R instruction. And how many bitwise invert register R instructions are there?
2.
There's 2. Okay? Now look at this. Let's go down here to this unimplemented opcode non-unary trap instruction. What is its instruction specifier? 0011 0 A.
There's 8.
There's actually 8 of those instructions. Are you with me? Why 8? Because it could be 0011 0 0 0 0, 0011 0 001. Are you with me? So that AAA, there's 8 combinations, right? Does everybody see how that works? And here's return from call with n local bytes. How many of those instructions are there? There's 8 of those. There's 8 of these, or 8 of these. Oh, how many load register R from memory instructions are there?
16.
There's 16 of them. All right, so all the possible combinations of ones and zeros are represented here, as long as you recognize that the R's and the A's could be either zeros or ones. Does everybody see how that works? So here is a picture of what I already drew on the board, figure 4.7. The two kinds of instructions. We have a non-unary instruction has an instruction specifier and an operand specifier, whereas a unary instruction has just an instruction specifier. And now what we're going to do is we're going to learn what these AAA fields are. A stands for addressing. Are you with me? Addressing. So there's 8 combinations of 3 bits. And here's a table, figure 4.8. It shows the addressing AAA field. Now, each one of these addressing modes, we're going to learn what they do. We're going to learn what all of this stuff does eventually. Right now, the only thing we have to learn how to do is identify the field and say, and look up from the table of what it is. Are you with me? Is everybody clear? So if the AAA field is 000, that means immediate addressing. If the AAA field is 001, that means direct addressing, and so on. So we've got direct, stack relative deferred, index, stack index deferred. We will learn what all of those mean. Each one of those we will learn what in the course of the course. Does everybody see how to read the AAA field? Okay, now remember some of those instructions had just one A. Remember it was the branch unconditional, had something other than A. Well, if there's just one A, then if it's 0, that's immediate addressing. If it's 1, it's indexed addressing. So it has a slightly different, it has a different meaning. So everybody, I mean, it's coded differently from if it's a 3-bit addressing field. And remember some of those had the R field in it? R is the register field, register R field, and they only have 2 options. If R is 0, the instruction operates on the accumulator, and if it's 1, it operates on the index register. Now, where is the accumulator?
In the CPU.
Yes, and where is the index register?
CPU.
In the CPU. Does everybody see how that works? All right. So now I think, so here is an example of figure 4.9 of some instructions stored in main memory. And I think what you had to do for your exercise is you had to identify what the instruction was and what each one of those fields were. Is that right? Mm-hmm. So do you see how to do it now? The way you do it in this figure 4.9, let's look at the instruction specifier. Okay, so the instruction specifier here says what? 1000, 1000, 1101, 1101. So what you would do is you'd go back here to this instruction set, figure 4.6, and we have to scan down until you get to 10001. So where is 10? I'm going to scan down here. Next one. Where do we see a 1000?
Subtract from register.
Subtract from register R. So now we see that if it's a subtract from register R, it's this part says what it is, right? And then what's the next field?
R, so it's
R. So
index register.
yeah, so this is R, and then this is the what?
Triple A.
Addressing mode, right. By the way, this part of the instruction, that this part right here of the instruction specifier, this is called the opcode. It's short for operation code. Are you with me? This is the opcode. This is the register R field. And this is the addressing A field. And this whole thing is the what? What's this whole 8 bits? This whole thing is the what? Instruction what? No.
Machine language.
The whole thing, the whole table is the instruction set. It's the set of all the instructions. Yeah, what did you say?
Machine language instructions?
Instruction specifier.
It's the instruction specifier. Is everybody clear? This is all just vocab. Okay, so with that in mind, now are there any questions about how to do the homework exercise? Were you able to sort through all that? I think what it gave you was, didn't the problem give it to you in hex?
Yeah.
And then from hex you had to do, expand it out to binary, and then you have to go look down and find out,
What does it do?
yeah,
What does register
R,
What does
yeah,
specify?
yeah. So it's just mechanical, right? That's mechanical, that's how it works. Are we good? Okay. Now what we have to do is, for your next assignment on Thursday, you're going to write a machine language program. So now what we have to do is we have to learn how these instructions, we have to start learning the instructions in the instruction set. Okay? And we have to keep in mind that each instruction is coded like this. You know, it has this coding scheme, right? With that. By the way, okay, now that we've defined what the opcode is, let's take a look at this figure 4.6 again. So you see this branch unconditional? How big is the opcode of the branch unconditional? How many bits?
4 bits.
No. Not for branch unconditional.
Oh, 7
Oh,
bits.
7.
7 bits. Yeah, the opcode is 7 bits. And let's go down here to the unimplemented opcode unary trap.
6 bits.
That's a 6-bit opcode. You see what I mean? And then down here, the return from call with n local bytes. How many bits in the opcode?
5.
5 bits. So the size of the opcode actually changes, you know. This is called expanding opcode. This feature.
What does the opcode stand for? It's the operation?
Operation code, yeah. That's the set of bits that tell you what the operation is. You see what I mean? And the reason it's called expanding opcode is because the number of bits that tell you what the instruction does, sometimes it's, in fact, what about for the stop instruction?
It's all 8.
Here, all 8. Yeah, see. Okay, is everybody good? Okay, so now let's start learning what the instructions do. The first instruction that we're going to learn is the stop instruction. So the instruction specifier for the stop instruction is 0000, 0000, and what it does is it causes the computer to stop. Now, this is the most unrealistic instruction of all the instructions in the instruction set for PEP 8. Because does a CPU ever stop? It actually not. Well,
If you shut off the power,
you shut off the power. It doesn't stop itself.
Okay.
You see what I mean? The mechanism to shut the computer down comes from external.
Hardware.
Well, it comes from an external. I mean, when you do. Well,
So does
I take it back. Yeah.
CPU, does that tell the CPU to turn off, and then this instruction
No. What I'm saying is no realistic CPU
ever calls?
even has a stop instruction.
Oh, okay. But because we're virtual, we want to be able to stop.
Because we're virtual, we want to be able to stop it. Yeah.
Okay.
Yeah. But this is the most of all the other ones are very realistic. They closely match. What I did is I picked all the representative ones, that are in the instruction set. But this is the one that's the most unrealistic of all. Because what happens is when you select shutdown, on the computer, then what it does is it goes through, and the CPU, the shutdown program goes all the way through, and then it sends a signal to another part of the motherboard, and then that turns it off. So it doesn't actually say stop. It sends a signal to another part of the circuitry to actually turn off the power. So there is really no, but anyway, that's for us. Now, here is, the next instruction is called the load instruction. And the load instruction has instruction specifier 1100, and then it has one register specifier R, and then an AAA. And what this does is this loads one word. Oh, how many bytes is a word?
2.
2 bytes, yeah, okay.
Was that an
Another
actual
vocab.
term?
Yeah, it is.
A word term.
Unfortunately, how many bytes are in a word depends on the manufacturer and the CPU. So on some computers a word is 4 bytes. It's hardly ever 2 bytes anymore. Used to be, but it could be 4, it could be 8, it could be 16. It depends on the manufacturer. Okay, so it's not a standard. This 2 bytes in a word is not standard. And what is this row of symbols down at the bottom?
Pseudocode?
No, it's not pseudocode. What kind of code? It's not.
UML?
No, it's not UML. Come on. We've done this.
Specification.
No. What does it look like with the left arrow? What does the semicolon mean?
It's not specification.
That means that you do the first one.
Register transfer language.
Register transfer language. RTL. Are you with me? Now what does the semicolon mean?
You do the left one and the right.
Yeah, that means sequential. And what does the comma mean?
Simultaneous.
Simultaneous. And what happens? What does this RTL specification say that load does?
Operand's transferred from
The operand gets transferred to what? Register R. Okay? And how do you know which register it gets transferred to? What did we say the R? What did we say about the R?
Zero.
If R is what?
0.
0, it goes to the where?
Accumulator.
It goes to the accumulator. If R is
1.
1, it goes to the
Index.
index register. Remember that? Okay. Are we good? Okay. And now what is this N? That's the what?
The first bit, negative.
That's the negative bit. Yeah, that's the N bit. So the N bit gets changed. And what's the Z stand for?
The 0.
That's the 0 bit. Okay? So here is an example of how this load instruction works in figure 4.11. Now watch. 4.10 and 4.11. Now watch. So if you have if you have in hexadecimal in hexadecimal, if you have the machine language C1004A, do you see how you could expand out C and the 1 and the 0 and the 0 and the 4 and the A? And then do you see then that you could look up in the table that 1100 is the opcode for load, and the 0 would be the R, and the 0001 would be the AAA. All right? Then do you, so now because R is 0 in this example, what does that mean?
It goes to the accumulator.
Accumulate. And what is what is for AAA being 001? Let's look that up. Here, what does 00001? That's direct addressing. Okay, so now I'm going to lay it on you. What is direct addressing? Direct addressing means that the operand specifier is the address of, in memory, of where the operand is. Are you with me? Do you see that the operand specifier here is 004A? That means that in main memory, there's a cell in main memory at address 004A. So do you see that in the bottom part of the slide, we have the CPU and memory with the bus below it, right? And in main memory, there's the content 92EF, and that's at address 004A. Now let's suppose in the CPU that the original content of the accumulator is 036D. If we execute this instruction, the C1004A instruction, what will that do? What will it do? Here is shown right. What is it? From where to where? It will go to that location in memory. Are you with me?
Take it from that location.
Take it from that location, and where will that data go? Over the bus, into the accumulator. And what will happen to the original content of the accumulator?
It'll be replaced.
It's wiped out. Gone forever. Now, does everybody see how that worked? Good. We'll continue this next time. But you got it? Okay, good. All right, good deal. See you next time.